subhanallah, alhamdulillah, wa la ilaha illallah, Allahu akbar, Allahu la quwwata illa billah azim. For information, the lecture slide you can obtain from our Ulam portal. I also upload this kind of the slide at our WhatsApp group. Okay, so let's say if you have any problem, just let me know. Okay, so to the topic is the introduction to NP problems. Okay. Okay, so this is the learning outcome for today. So at the end of this lecturing, the student will able to understand the concept of SAT and apply the concept of SAT to the real problem. Okay, so this is the outline for our lecture today. So basically, I divide into 8 part. First part is motivation, why we need to learn this thing. Okay, second part is the problem complexity overview. What is the problem complexity? Part 3 is I will brief you about the logical theory. Actually, in our school we already learned this thing, but however, I will do a little bit flashback about the logical theory. Maybe most of you already forgot this kind of the things. Okay, for part 4, we'll describe about the accessibility of SAT. Okay, part 5 is a traveling assessment problem. So we will learn about the implementation of NP problem in TSP problem. Part 6 is implementation of the SAT in the graph coloring. Part 7 is implementation of the SAT in Edquin problem, and last one I will close with the summary. Okay, so basically we have a 3 case study: TSP, graph coloring, and Edquins. Okay, so semua boleh dengar Okay, so we go to part 1, motivation. Why we need to learn this thing? Okay, firstly, computing is expensive. Okay, so AI progress is often limited by compute than by ideas. So high performance hardware, especially GPU, remain costly. GPU-based PC on major retailers such as Amazon typically range from 100 to several thousand of dollars. So this cost restricts experimentation, model scale, and training frequency. Estimating compute requirement early is essential for sustainable AI development. Why I say computing is expensive? So as we know, the price of the gaming laptop, the lowest price, okay, is a 3,000, if I not mistaken, 3,200. The entry level of the gaming laptop, 3,200. Is it expensive? Yes, it's expensive. It requires thousands of ringgit in order to compute the AI algorithm. Okay, so that one is just an entry level computing. Okay, but however, if you want to compute on the server, such as Amazon, they charge every second of the computing. Okay, so that's why I'm saying computing is expensive. So the second we need to pay. Okay, so that's why we need to learn this kind of the topic. Okay, understand? Okay, it's not about we want to reduce the cost. It's all about we aware what is the things that we already develop, because we are here, we want to develop the AI algorithm, right? So when we develop AI algorithm, we need to know the project cost of the AI algorithm development. Okay, so this kind of the topic, we will learn about the awareness about the how much computing we require. If let's say if we develop an algorithm like this, okay, is it expensive? Is it cheap? Okay, it's not about reducing the cost, but it's all about the awareness. Okay, and then the important the estimating the computing. So as AI developer, he or she must estimate the computational demands during designing algorithm. So the estimation help to select suitable computing device. Proper estimation support efficient and flexibility AI development costs. Okay, so we go to part 2, problem complexity overview. Okay, so computation problems are categorized into complexity classes based on the solvability and efficiency. So some problems are fundamentally unsolvable by any computer algorithm. Other problems can be solved efficiently with algorithms that run in polynomial time. A third category includes problem which no non-efficient algorithm exists requiring exponent time in the worst case. Complexity theory provides to classify this problem and understand the limit computation. Okay, so basically there are three general problems that we will learn today. So first we call it NP, second is NP complete, third is the NP hard. Okay, so this is three class of complexity computation. Three class of the complexity computation that we will learn: NP, NP complete, NP hard. Okay, so NP is the solution that can be verified efficiently in polynomial time. NP complete is a problem that can be solved efficiently. Okay, NP hard is the problem at least hard as an NP complete problem, but don't have to be an NP that has been solution that can be verified efficiently. Okay, so as conclusion, NP is a satisfactory solution that can be verified in within polynomial time. NP hard is the no solution that can be solved in the polynomial time. NP complete is combination of NP and NP hard. Is a satisfactory solution can be verified greater than polynomial time. It's a confused, right? The confused statement, right? But actually, I try to show to you what is the similarity between this kind of the classes, and also want to show to you about the difference between three classes. Okay, so now we go to the design. Okay, how it looks like. So as we learned previously, okay, as I mentioned before, there are three classes: NP, NP complete, NP hard. If you want to understand more detail, NP, the condition in NP is first satisfiable. So that means the problem can be solved. Okay, in terms of problem time solving is much less than n power of 3. Okay, which is polynomial time, n power of 3. NP complete, the problem must satisfiable. It means the problem can be solved, and the time to solve the problem is n power greater than n power of time, which is the problem can be solved greater than polynomial time, n power of 3. Okay, NP hard is not satisfiable. The problem cannot be solved, and time to solve that problem is greater than n power of 3. Okay, so this is the difference and similarity among these classes. Okay, any question so far? Can if you have any question, just let me know. Okay, so we go to part 3. Before we go in deep, I want to brief to you about the logical theory. Okay, because the logical theory actually is a fundamental things if you want to learn about the computation. Okay, okay, because all the computation will be presented in the logical theory expression or logical theory equation. Okay, so what is the logical theory basically? Actually, is a formal study of reasoning, inference, and truth. It provides structured method to evaluate valid and invalid argument. So it underpins disciplines such as mathematics, computer science, philosophy, and AI. Basically, it focuses on proposition, logical connective, and inference rules. So it also promotes precision, consistency, and clarity in reasoning. Okay, so the basic component in the logical theory, there are three things. Okay, so sorry, four. First is negation, second is and, third is O, and the last one is implication. Okay, so this is the basic operator that we will learn today. Okay, example of the propositional logic. Let P present database is connected. Let Q represent the SQL query execute successfully. So the statement P and Q, this one in P and Q. So database is connected and the SQL execute successfully. Okay, so if P is true and Q is true, those true is one multiple 1 equal to 1, because n can be the logic of n is multiplication. Okay, the statement P or Q means the database is connected or the SQL query executes successfully. Let's say if P is true and Q is false, so that means the answer is true, because P or Q all stand for plus. 1 plus 0 equal to 1 plus 0 equal to
1.
1. Okay, that's good. 1 plus 0 is equal to 1. Okay, and then the statement P then Q, arrow means then. Okay, if the database is connected, then the query executes. Okay, so understand so how we can convert from the logical expression to become a human words, and then after that we can do the calculation of the logical expression. Okay, so you need to remember n for multiplication or for plus. Okay, so this is the important things. Okay, so this is an example of the truth table, which is firstly you need to understand, and after that if you can remember, then it's better lah. Okay, okay, so start. Okay, Boolean accessibility problem. Okay, so right, start is all about the how to satisfy the Boolean problem. Okay, so Boolean satisfiable or simply said is a problem of determining if a Boolean formula is satisfiable and satisfiable. Satisfiable, which is means can be solved, which is means the output is 1. Unsatisfiable, the output is 0. Okay, if let's say if the question, we calculate it and the output is 1, so that means it can be considered is satisfiable. But however, if let's say if the calculation of the Boolean expression, the output is 0, all the output is 0, there is no 1, so this means we can simply say the problem cannot be solved or unsatisfiable. Okay, 1 means satisfiable, 0 means unsatisfiable. Okay, so we go to the what we call that example. Okay, so this is before we go in the example, so this is the step how to classify SAT into complexity classes. Okay, so first step is assigning a variable. Second step is create a hypothesis. Third is a proofing. Okay, if a truth table too long, so just predict whether proof or not via logical thinking. Fourth is calculate the computation through hypothesis. Fifth is calculate the computation of the polynomial time, and the last one is determining whether NP complete or NP hard. Okay, so how to determine SAT as an NP complete? So the first condition, the formula must be true. So at least 1 is 1. At least the output is 1. Second condition, if the computation cannot be solved in polynomial time, which is O n power of 3, where n is the input size. So if input x and y polynomial time is 2 power of 3 equal to 8, so then if total time is greater than 8, thus the condition 2 is met. Sounds like complex, right? But however, don't worry, I will provide the example. Okay, I will provide the example, no need to worry. Okay, okay, so we go to the example. So this is the important part, you need to master the example. Okay, let's say SAT is A or B and not A or C. Proof as SAT as NP. Okay, so firstly we need to know the variable that involved in that equation. There are 3, right? A, B, C. So that means we have a 3 input. Understand? Second is hypothesis. What is the hypothesis here? Basically, the hypothesis is the expression, the Boolean expression itself. So we just list down A, or B, and negation A or C. And after that, we come up with the truth table like this, okay? A, B, C, which is the input. And then after that, we calculate it. And then we obtain, there are 1, 2, 3, 4. There are 4 times the output is 1. So that's mean, what is mean? It means this kind of the expression is satisfiable. If let's say if all the output is false, it means it's not satisfiable. But however, let's say if only one got through, others is false, it also can be considered satisfiable. Okay, understand? Any question? No question. Okay, good. Okay, don't worry, we have a many example after this. And fourth, we need to compute hypothesis computation. Okay, so the formula how to calculate the hypothesis time is a 2 power of n. So what is n? N in input. How many input that we have here? 3, right? A, B, and C. So the hypothesis time is equal to 2 power of 3 equal to n. And then polynomial time. Polynomial time, how many? The formula is n power of 3, which is 3, n is input, 3 power of 3 is 27. As we can see here, since the hypothesis is stratified, because got true, right, in the output, and the hypothesis time less than polynomial time, so it can be considered as a n and p. Okay, that's all. Any question? Hello.
Sir, yang truth table tu kita kena buat sendiri ke?
We need to do ourselves. Okay, we need to do ourselves.
Okay.
But there is a case we cannot do our own because the expression is too long. If let's say is the expression too long, you need to use your own logical thinking in order to predict whether the output got 1 or not. For example, here we have a 3. Of course, we can do the truth table. But how about let's say if the input is we have a 10? Is it possible we can write our own truth table in the exam paper? Of course, it will difficult because it will took longer time to calculate by our own, right? So in that case, you need to predict the output by using your own logical thinking. Is it there is a 1 got true or not? Because the purpose why you need to do the truth table is you need to know whether the expression is satisfiable or not. Okay, clear?
Clear, sir.
Okay, thank you very much. Okay, so we go to the example 2. Okay, so this is the expression A or B and negation B or C. So we need to prove S and P. Is it NP or not? Okay, so firstly we need to list down the variable. How many variables that involve 3, A, B, C, and the hypothesis is A or B and negation B or C. And then we do the truth table. From the truth table, we can see there is 4 times we got the output equal to 1. So we can consider the formula is satisfiable. Okay. And then after that, we compute the hypothesis computation time, 2 power of n. So n is how many? 3 input, right? So we just replace 2 power of 3 equal to n. And then we compute polynomial time, n power of 3, which is 3 power of 3 equal to 27. Okay, so since the hypothesis is satisfied, is it satisfied? Yes, because we have the output is 1. Okay, hypothesis is right, and hypothesis time is less than polynomial time. Okay, and then we consider the problem that we need to solve here is NP. Okay, two condition. Remember, two condition. Hypothesis is certified. Hypothesis time less than point time, so it NP. But however, if the hypothesis time greater than polynomial time, so it will become NP, NP complete. Okay. Okay, we go to example 3. Okay, so this is the question. Okay, so as so as we mentioned before, so there are 3 variable ABC, and then we list down the hypothesis here, and then we make the truth table. So we found there are 4 times we got the output 1, so that means the formula is satisfiable. Okay, and then we calculate the hypothesis time is equal to 8. Okay, same also. Polynomial time is 27. So is it NP complete? No, it's still NP. Why? Because hypothesis is satisfied and hypothesis time is less than polynomial time. It's still NP. Okay. Okay, so now previously we just learned the fundamental, right? So now we go to a little bit, difficult. Okay, because we want implement the traveling assessment problem. Why we need to learn? Because in real life, we will calculate the traveling assessment problem through our phone, right? Why I say like that? GPS, like such as Maps, Google Maps, or maybe Waze. This kind of the application will compute your own traveling, right? So we need to know how much the Maps, Google Maps compute your problem. If you go from UTM to your own kampung, how much computation that required by the Google Maps or maybe Waze. So that's why we implement in this kind of the problem, so that you will understand why when you use Waze, you will use Waze application, why it took many computation, why your battery suddenly finish the electricity. So you need to know that. Okay, so before we go in deep, so we need to know what is the problem itself. So basically, traveling assessment problem is optimization where the assessment must find shortest possible route to visit list of city, at least one, starting from one city and returning to same city. So basically, is a classical problem in computer science. So basically, it's like this. So traveling assessment problem, a person or assessment required to finish all the shortest possible route, and at the same time need to visit all the city. Okay, so let's say if we have a 3 cities, so the example city A, city B, city C, and the route is HA, HB, and SC. Okay, so here we need to know whether this one is a NP normal or NP complete. Okay, so first one is a variable. What is a variable that involved in this expression? HA, HB, and HC. Okay, and then the hypothesis. Okay, hypothesis is a Hamiltonian tower. A TSP tower visit. The assessment need to visit city A, city B, and city C. So that means there are 3 routes that need to follow, which is HA, HB, and HC. Okay, so that means if the assessment need to complete all the city visiting, so the assessment need to visit city A, city B, and city C, and at the same time need to use the route of HA, HB, and SC. So that means HA, HB, and SC. So you see the word, I'm using N. So since I'm using N, so the expression should be F equal to A, N, B, and C. Okay, understand. So this is the hypothesis for this kind of the problem. Okay, and after that we come up with a truth table. So here we have a 3 input A, B, C, and then we calculate it by using n, get of n. Okay, and we can see here there is a one solution that satisfies this this expression, which is A equal to 1, B equal to 1, C equal to 1. Okay, so it yield true. So it can be either F equal to A and B and C is satisfied. Okay, so we calculate the hypothesis time, 2 power of 3 equal to 8, polynomial time 3 power of 3 to 7. Again, it can be considered as a NP problem. Why? Because hypothesis is satisfied and hypothesis time is less than polynomial time. Okay, so we make the problem become a little bit difficult by adding new city. Okay, previously we just have a 3 city, right? Now 4 city. Okay, so in this example we need to determine whether this one is a NP problem, normal, or maybe NP complete. We need to know. Okay, first is a variable. Okay, what is variable that involve? HA, HB, HC, and HD. So hypothesis is A and B and C and D. Okay, HA and HB and HC and HD. Okay, and then we provide the truth table, calculate the truth table, and we found the expression of F equal to A and B and C and D is satisfied. Why? Because the output is equal to 1. Okay, and then we compute the hypothesis time is equal to 16. Why? Because we have a 4 input. Polynomial computation is 4 power of 3 equal to 64. So hypothesis time less than polynomial time is a NP. Okay, so we go to the proceed with the next problem, graph coloring. Okay, so what is graph coloring? So graph coloring refers to problem coloring vertex of a graph in such way there are no two adjacent vertices have same color. So they are so-called vertex coloring problem. So if coloring is done using at most m color, is called m coloring. Okay, so we go to example. So for the graph coloring, there are 3 nodes has been drawn between themselves, prove such, and determine whether it is an NP normal or NP complete. So here we need to provide truth table. Okay, so there are 3 nodes A, B, C. Okay, we need to make sure the color of node of A, B, and C is not same. Okay, so what is the variable here? So basically there are this is the variable. CTA become red, CTA become green, CTB become blue. CTB become red, CTB become green, CTB become blue. CTC become red, CTC become green, CTC become blue. So this is the variable. So how many variable? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a 9 variable. Okay. And then the hypothesis. Okay, so this is hypothesis. There are 3 hypotheses that can complete the graph coloring. So every node has at least 1 color, either R or G or B. So maybe for the node A R or A or G or A or AB. Okay, so that's mean node A can be R or green or B. Same goes with B, can be red or green or blue. C can be red or G, green or blue. Okay, this is represent for the statement of every node has at least 1 color. Okay, and then at the same time, second of this is that every node cannot have more than 1 color. Okay, less than, okay, negation as we know, okay, there are 3 variation, right? Red, green, and blue. Okay, so every knot cannot have more than one color. It means knot are, this one for knot A, not red or not green. Okay, so that means it's a blue. Okay, so this is a ni. Same goes with the next hypothesis. Neighbor chord knot cannot share same color. So that's mean, let's say if the knot A become red, knot B should be, not should be is a red also. So we present it become a Boolean expression here. Okay, this one is for red, green, and blue. Okay, after that we combine it. Okay, all of the expression we combine become one expression. So that's mean how to combine, we join as a n. Okay, so this is the way how we combine it. Okay, and then we make as a truth table. But the problem is when you want to compute the truth table is very long. Okay, we need to use a software. We cannot use a manual, I mean like handwriting, to compile the truth table. Okay, but however we need to know how many combination here, because it greater 2 power of 9. Okay, 2 power of 9, 512 combination. So by using try and error, so let's say this one is a logical thinking. We just try and error. Let's say AB1, BG1, CR1. So the output become 1. Okay, so it is a satisfied, and then we calculate the harvest time is a 512, polynomial time is a 729. So since the harvest is satisfied, harvest time less than point time, so it's NP. Okay, so this is example 7. Okay, example 7. So there are 4 knot. Previously 3 knot, but this one is a 4 knot. Okay, so 4 knot, so we need to know the variable that involved. So since we have a 4 knot, so that means we have a 4 times 4 is a 16 input. A become red, A become green, A become blue, and become yellow. Okay, same goes with the knot B, knot C, and knot D. Okay, and after that we using same hypothesis from the previous one. So that means, let's say if the question, I mean the final exam question asking about this kind of the problem, so that means you need to make sure you have a same hypothesis like this. Every knot have at least one color, every knot cannot have more than one color, neighbor knot cannot share some color. Of course it will long. Okay, of course it will long. Okay, but you need to be a patient if you want to list down here. Okay, and then after that you combine all. Okay, combine all the expression. Okay, through AND get. Okay, through AND get, and after that you need to come up with the truth table. Again, since the truth table difficult to return because it's too long, it will generate 65,536 combination. So by using logical thinking, output will be certified if, let's say, if the input is below than 0. Is the input as below is 0 lah. So except AB1, BG1, CR1, DY1. Okay. So for the this time is a 65,536. Polynomial time is a 4,096. So since hypothesis is certified, hypothesis time greater than point time, so NP is complete. Okay. So here hypothesis time is greater. When the hypothesis time is greater than polynomial, so it become NP complete. Okay. Okay, now we go to the equine problems. Okay, equine problem. Okay, so equine problem is a classical combination and backtrack problem in computer science and artificial intelligence. Okay, if too many queens in the chess game, the game become stuck or draw and lost. I think previously we already learned this kind of the problem, right? Okay, it's all about the chess queen problem. Okay, because we want to avoid this kind of the problem in our game. Because let's say if we not avoid, the game becomes stuck. Because so many queen, right? The game becomes stuck. Or maybe the game become draw, or maybe become lost. So we need to avoid this thing happen in our chess game. Okay, so let's say, okay, we go to the example, straightforward the example. The example you need to understand so that you will understand the equation itself. Okay, for n queen, okay, which is a 2 queen, so there are 9 block of chess map. Proof start and determine whether it's NP normal or NP complete. Provide also truth table. Let's say like this, okay, so this we have a 2 queen, and then we want to estimate whether this thing is NP normal or NP complete. Okay, so we go to variable. So what is the variable involved? So basically there are 1 2 3 4 9 variable involved: A B C D E F G H I. Okay, and then second, what is the hypothesis? Okay, no attack at row, no attack at column, no attack at diagonal, no attack at row, column and diagonal. Okay, so we conclude all the things, and then we come up with the truth table. Okay, and we found, let's say, if A equal to 0, B equal to 0, C equal to 0, D equal to 0, okay, E equal to 0, F equal to 0, G equal to 0, H equal to 0, I equal to 0, so the output will become 1. Okay, and then we found that hypothesis time is less than polynomial time. Okay, so here we can consider is a this one is a NP complete. Okay, okay, so for example 9, we have a 3 queen, and then we make the map, I mean the game, become larger. So those the input that involve is also many also. We have a 4 times by 64. Okay, sorry, 16 input here: A B C D E F G H I J K L M N O P. Okay, and then there are 3 queen involved on there. Okay, and then after that we come up with the hypothesis. There are 4 hypotheses here. Okay, no attack row, no attack column, no attack diagonal, no attack at row, column and diagonal. Okay, okay, and then we come up with this one, the hypothesis. Of course, is too long, and because it will it will make the combination 65,000 something. So we need to try and error whether the output is 1 or not. Okay, and then we found, let's say, if all the input is 0, okay, so the output become 1. Okay, and then we see the hypothesis is certified. Okay, so hypothesis time we calculate it 65,536. Polynomial time we calculate it, it become 4,096. And then since hypothesis is certified and hypothesis time greater than polynomial time, so those NP is complete. Okay, so now we come to the end, part 8, summary. Okay, so we learn about the concept of SAT and application of SAT in the real problem. Okay, okay, so I stop it.